Hello, everyone. Welcome to today's webinar. My name is Randy from Element 14, and I'll be your host today. Today's presentation is from Texas Instruments. It's called How to Extend Flight Time and Battery Life of Quadcopters and Industrial Drones with Electronic Speed Controllers. This webinar will be presented by Kristen Mogensen and Kevin Stoddard. Kristen is a system engineer for TI's industrial motor drives, focusing on both hardware and software. He has worked in this role since 2014. He began his career at Texas Instruments in 2008 and has held various technical roles since joining the company. Kristen has studied electrical engineering at the Technical University of Denmark. In 2008, he received his Master's of Science in Electrical Engineering. Kevin is a systems engineer for appliances and power tools. He has worked in this role since 2014. He came to Texas Instruments after receiving his Master's of Science in Electrical Engineering and has held various technical and marketing roles at TI. At the end of the presentation, there will be a Q&A session. You can ask questions in the Q&A window of the WebEx screen. So let me hand it over to Kristen and Kevin for today's presentation.
Hello, my name is Kristen Mogensen. I'll be starting the presentation and then I'll be passing the presenter rights to Kevin at the midway of the presentation. So today the agenda will be we'll be first discussing a high-speed sensorless FOC design for drone ESCs, and then we will be discussing a battery-packed solution for drones from Texas Instruments. For the high-speed sensorless FOC for drone ESCs, we'll be having the following agenda. First, we'll have a quick overview of a drone, so we can have a short understanding on what are the specific modules that you need to build to actually build a full drone. Then having discussions on trapezoidal and sinusoidal control considerations. Then what type of software what type of software do you need to consider when you do your design, both before you get started but also during this whole design phase. Then what test results and also the test setup that I used to test this design, and then a design overview telling you a basic recap of what the design can do and perform. So from a drone perspective, you have basically first the flight controller of the drone, which is basically it accepts all the commands from the remote and is basically the one that is getting in the feedback, but also getting in the control after, so basically passing out the control to the motors and also getting the feedback from all the sensors that is implemented in the drone to ensure that it is flying correctly and it's flying as expected. Then you have a gimbal controller. The gimbal controller, depending on how good or let's say how professional it is, it basically can consist of anything from 1 to 3 axes. Then there is also a camera module. And this part of the drone we would call payload. Basically, from a payload perspective, this can be anything that you would need, that you would say this is part of what my drone is supposed to be doing, and it can be anything from a video camera to potentially building on a thermal camera, a radar sensor, whatever you want, you can put on here as a payload, right? Then there is the vision and sensory systems that you will connect with the flight controller, and this is basically done to give the drone a knowledge of its surroundings so that it can basically avoid maybe flying into a wall. If it knows the wall is there, it will not allow the user to fly it closer to the wall than it knows it's safe. Then there is the battery pack. And then in the end, there is the ESCs, also called electronic speed controller. Depending on which type of drone you have, today we'll be talking more on it from a quadcopter perspective. So you would have 4 motors. But of course, if you have only a normal plane kind of configuration, you would only have 1 motor. Here, typically, what you see today is it's a brushed DC motor you'll be using or a trapezoidal controlled motor. And here you need this motor and having speed control on this motor to change your thrust and direction change of the drone. This part of the drone we call the flight system. Then of course you also have a remote control, and here you basically, it takes the inputs from the drone and also gives back inputs to the drone how to fly. And of course that controller also needs a battery pack. And this we call the remote. For our presentation today, we would focus on the ESC, or at least this part of the presentation. Later we would then focus on the battery management. So for the ESC, there are some, basically depending on what type of motor control you choose to use, you can improve the efficiency of the motor and also the speed dynamic performance that you have of the motor. As typically you see that a trapezoidal control is used to drive the motor, what you see is that this trapezoidal control, intrinsically due to the way it's done, has a torque ripple. If you move this to FOC control, you remove this torque ripple, and this will give you a more smooth control, and due to the way FOC works compared to trapezoidal control, you also gain a dynamic performance of how the speed will change or how quick you can react to speed change. Of course, moving to FOC also creates new challenges. For instance, FOC compared to trapezoidal control, you need a more accurate angle, and you can of course do this by adding a sensor, and this sensor is expensive, so of course it's not really a solution. Therefore, if you do FOC, it's only really interesting if you can do it sensorless. You can do this sensorless, and here you would need a back EMF based sensorless algorithm, which we'll also be discussing a little bit later. So here what we show is, if you have a typical trapezoidal ESC, these are the main components you would need to make the motor move. So at the end of the day, what you see is you have three half bridges that are either connected with FETs. This can be external or internal. Typically you would have external FETs due to the fact that you are simply driving so much current you cannot dissipate that power inside the package. So you would try and separate them by moving the FETs out. What you also see is you have one current sense amplifier, and then potentially voltage sensing and also DC or you would have voltage sensing and also potentially DC link sensing, depending on how you do your control mechanisms. If you go to sinusoidal control, what you see is it doesn't really change that much. The biggest change is you need to measure three-phase voltages, or you need to measure the three phases instead of only measuring one combined phase current of the low side. So now going into more kind of a comparison that you can understand the differences between trapezoidal and sinusoidal from a control perspective. So what you have is, with trapezoidal control, what you see is that you have a 60-degree angle measurement. So basically every 60 degree you will commutate, and with this commutation your motor will move. For a field-oriented control, what you have is you have a real-time accurate angle measurement, so your angle needs to be a lot more precise. Depending on how you do the sensorless control, you'll have different back EMF-based control techniques. For the trapezoidal control, typically you'll have the zero crossing technique. There is also a different approach called InstaSpin BLDT, which is doing integration. Then if you move over to FOC, what you have is you have a sliding motor technique, and then there is the option of using the InstaSpin FOC, where you would be at the end using the TI fast algorithm. So when you do trapezoidal control, what you see is that you have the need of 3 phase voltages and potentially an optional one single shunt measurement. And again, for InstaSpin BLDC, you'll see you have the same setting. If you go for the sliding mode observer, what you see is you need the DC bus plus 1 to 3 shunt measurements. Here, depending on how many shunts you choose, you also limit the bandwidth or the PWM duty cycle you can use your PWM controllers at. So you're kind of limiting how much of the DC V bus you can use for your motor control. So it's some considerations, but in the end you have a choice. For the InstaSpin Fast, you need 3 phase voltages, the DC link voltage, and 2 to 3 shunt measurements. Again, here the shunt, it's the same discussion. You will limit yourself, but it's a choice. You don't necessarily need to, then you can do 3 shunt measurements. What you see from a torque performance and also a speed performance is that from a trapezoidal perspective, due to the way the zero crossing technique is done, what you have is you have a poor dynamics, meaning that when you do a speed change, it will take you time to react to the speed change. If you move to InstaSpin BLDC, you will see that you are more robust to load changes, but also have a better dynamics. You can react quicker to speed changes. What you have from a torque perspective is you have a high torque, but you have a torque ripple because you are commutating at every 60 degrees. And this will give you a torque ripple which will also decrease your dynamics here on the torque performance. Then going into FOC, what you see is that for a sliding mode observer, you have a typically poor low speed performance. This of course also depends on how, let's say, advanced your sliding mode observer is. Then you'll have a medium dynamics on your full speed, on your full speed range. One thing you will have for sure is it's hard to tune, and you need to tune this for different load cases and also different speeds to make it run stable over your full dynamic range, the sliding mode observer. Moving to the InstaSpin TI Fast algorithm, what you see is you'll have a best low to high speed performance compared to the other 3 options. You have the best dynamic performance, and the really nice part is from an angle perspective, the sensorless part of it is self-tuning. So you have a identification protocol that you use to identify the motor parameters. As soon as you have them, you don't need to identify the motor again. You just put them into your system and you don't have to think about the angle measurement again. For the torque performance, what you see from from the FOC perspective, you see you have ideal torque control, which means low noise, smooth operations, and the best dynamics. Of course, here part of it is also your motor. Your motor for trapezoidal control would work best if you have a trapezoidal wound motor, and of course, again, the same for the FOC. If you have a sinusoidal wound motor, you will get the best benefits out of the system. You can, of course, always do them crossed, but of course there you will see some performance degradation of your system. From a system cost perspective, you see here trapezoidal control, it's the same, and here you will add additional measurement for the current shunts. So you will have a little bit additional extra cost here. Now looking into the challenges of FOC control, you have 3 aspects you need to consider. First, you need to consider the PCB as such. What type of power stage do I need? What type of voltage current sensing do I want to do? How good does it have to be? All these type of considerations you need to do up front. Then from a software perspective, you need to build your FOC part. And when I say FOC, I mean just the Clark, the Park, the PI controllers, the acceleration, the trajectory definition. All of this is basically standard. And then a second part of that's also software is you have the angle estimation, but in theory you could also do it with a mechanical sensor. Going a little bit more into details with the software. From a software perspective, you also need to know that your the controller you use has the PWM features you need to do deadband, to have the deadband done correctly. Can you trigger the A to D sampling at the times you want? Can you sync all the PWMs at the same time to be able to use the PWM patterns as efficiently as possible when you drive your MOSFETs? Then what type of electrical speed of the motor do you need? The quicker you need to run the motor from an electrical standpoint, the quicker you need, the more processing power you need, because you need to sample your current measurement, or you need to be able to process your current loop enough times, enough that you can basically have a stable speed control for the high speed you're running it at. Then of course also, can you tune your PI controllers easily, or is it something where it's trial and error and hope for the best? And then the last part from a software perspective is, as I was saying earlier, we're talking about a back EMF based sensor. When the motor is not turning, there is no back EMF, meaning you cannot get the angle at zero. So you need to start moving the motor first, and then after a certain point you pass over from an open loop control to a closed loop control. This part of the algorithm you also need to build into your software template. Then from a hardware perspective, you need to consider the voltage rating, the voltage and current sensing. You need to consider the FET ratings. Can they do the currents and voltages you need? You need to consider the efficiency of your system from a conduction and switching perspective. And then of course, what type of protection do you want on your system if a failure happens? Then from an angle perspective, do you do mechanical sensor or do you do an estimation algorithm? And with the estimation algorithm, you need to tune this algorithm for the entire speed range, and you also need to know your motor parameters. So choosing the InstaSpin FOC perspective, you basically have the fast software encoder, and this will take out this part of the equation from your design considerations. This is done for you already. So then the second part comes, as I mentioned before, you don't need to do anything from a angle estimation perspective anymore, but there is still work to be done. You still need to adjust your PI controllers here, your PI speed and the PI for the current loop, to ensure that your system performs exactly as you want, because of course you know exactly how do you want your motor to spin. Then doing this, what we also added into the MotorWare library is a tool or a project where you can basically real-time, with the hardware you're using, with the motor connected, you can real-time see your motor do a step response in current, and also tune this step response to give you the current step response that you believe it will suit your system the best. At the end of the day, when you look at the high-speed motor that I was mentioning before, you basically see that every 833 microsecond, you basically have you're basically turning the motor one turn, right? Meaning, for your current control to be able to react to this very high speed, you need to run the current loop very fast. And for this system, we tested it up to 22 kilohertz current loop, and that basically means roughly 44 microseconds. So this basically enables you to say that my step response here, you see that roughly from, I say I want a new current from the current for the old current to the new current to be applied or to be adjusted for the PI controller, it basically takes me roughly 400 microseconds. And you see that with 800 microseconds, this is more than enough time for you to react quick enough for these high speeds. And then, meaning at the end of the day, this will enable you to have the stable step response for the electrical frequency in your motor. And this is something you need to basically time for your system. Of course, making this ultra fast will also generate maybe some efficiency losses that you can compensate by making it slower, but this is part of the dynamics of your system that we would not be able to know, and this is where you need to basically tune this motor with this current tuning for the best performance of your system, right? Then going into the next step, what you saw before with the current and speed controller, we have them in a cascaded control. So what you need to do is first tune the current controller to what you believe is the best setup, and then what you do afterwards is you can tune your your speed controller. Here you see I tuned the speed controller for a slight overshoot here for the high speed signal, and then when you have done this speed control, what you do is you can basically go for the full speed range of your motor, and what you see here is that with a very high dynamic performance you can go from minus 8,000 RPMs to plus 8,000 RPMs within 400, roughly, let's say 500 milliseconds. And this basically also, you see here you have an acceleration of 3,600 RPMs per second on the trajectory when you change the motor speed. Here you see a slight overshoot. Of course, adjusting the PI controller for the exact right performance you will be able to compensate this part of it. Then showing a little bit of the system of how we tested it, what we saw was that when you run this propeller and you put it directly at the table, what you'll see is the turbulence that the propeller is generating will basically also create instability in your speed performance, because it's basically pushing down the air so much that it will affect how the propeller is moving. So you will see instability of the propeller or of the motor due to this air movement. And this we compensated by doing the setup here, where you can see that it's kind of looking more like a drone, and here you can see the air can move away from the motor, right? And then you see here the boards we used, the power supply, and then I connected it up with the PC using Code Composer Studio. Here it's basically connected directly with this launch pad, and the debugger is already included on that board. And just to give you a slight idea on the motor size, but since you already know drones, you know how small they are, but you basically see here they are like very, very small. From a design perspective, what you see is that you see a very high performance system solution for a drone ESC, where you basically have all the interfaces you need to do your motor control for a sensorless FOC control. Also here showing the TI Fast Observer that you can run at these very high speeds, and we show the high dynamic performance from 1K RPM to 10K RPM. To do this change, you can do it in less than 200 milliseconds. Well, the motor we tested with is basically a 6-pole pair motor, and there we ran it at 12,000 RPMs at the maximum. What we used is the standard TI EBM, so basically the InstaSpin Motion Launchpad and the DRV 8305 booster pack. And these two are standard. You can put them together. They're already included into the hardware. And reading the design guide, I also explain a little bit how you change the DRV booster pack to be able to include your higher frequency motors, the higher frequency that the motor will be running at. Normally that board is built for 300 hertz motor, and changing that up higher, you need to change the filters of the system to be able to not attenuate the signals too much when you run it fast. Then very easy firmware example from for the C2000 Launchpad using Motorware. The board as such, due to the booster pack, supports from 2 to 6 cell LiPo batteries, and the phase current rating is 15 amp. This can be also changed adjusting the FETs used on the booster pack, and also here you need to ensure that the higher currents are also supported by the shunt you're using. Then some of the benefits you have in the system is what I was talking before about 22.5 kilohertz PWM. Now you see why, current control. Now you see why, because I run it at 45 kilohertz PWM. And then I divide it down by 2. This is done all in hardware, so you are not losing any processor power doing this conversion. And then at the end of the day, what you get here is you get very fast to market with very limited no tuning on the sensorless algorithm, and you can very quickly tune your motor setup with the specific propeller you want to use for the best performance you can get. And for a little bit more information on how everything is done, you can go to the TIDA 00916, and here you find the tool folders design guide explaining some of the tests we did to show performance and how we use the system. And here is a little bit on the data sheets. But here also you find the links to the 2 EVMs that we use that you can also buy on TIE Store. And that was it from my side on the ESC on drone, and I will now passing the presenter rights to Kevin. So.
Thank you, Christian. So I will now continue with the battery pack section of the presentation. So Christian showed us the different blocks that you can have in a drone, and we will focus today on the battery pack section. So first, let me recap some of battery basic. Let's start with what is the open circuit voltage. So if we look at the voltage of a single cell lithium-ion, we can see that the voltage will go from 4.2 up to 3 volts. And we'll have this kind of shape with a steep curve at the beginning and at the end of the cycle, and then with a relatively flat plateau in the middle. One thing to keep in mind is that this curve is obtained at really low discharge current. And the cell will have an impedance modeled here by Airbat. And once we will have a charge or a discharge current going through the cell, we will have a voltage drop that will apply to the battery cell. This means that once higher is the discharge current, bigger will be this voltage drop, and quicker we will reach the end of discharge voltage, EDV. So that means that even if in theory my cell have a total capacity of Qmax, bigger is my current that I'm using to discharge it, and lower will be the capacity that I will be able to use. So this is something we have to take into account, especially in application where the current is high, or when the current is constantly changing, like for example in a drone, when we want to accelerate or go up or down, then this voltage, this current will constantly change, meaning that this curve will also keep going up and down, making it harder to estimate the remaining capacity. Another term I would like to talk quickly about is what we call C-rate, which is basically the discharge or charge current. And this is usually the current which is needed to discharge fully the battery in 1 hour. That's why when we speak about a current of 1C, meaning it will be, the battery will be fully discharged in 1 hour. If it's 2C, that means that it will be the current needed to discharge the battery in half an hour, and so on. State of charge, SOC, I will mention it also, so this is why I prefer to explain what's the acronym. One thing also important when we are looking for solution or discussing about battery pack is understanding what is S and P. So S is how many cells do we have in series, and P in parallel. Why is it important? Because it's not because you have two batteries that you need to have the same solution. 2S, 1P, so two cells in series, one in parallel, will have a higher voltage, a lower current. So this is the same power rating, but this is important when we are looking into the solutions. And last but not least, because I will also mention it later, CEDV, I mentioned before that EDV is the end of discharge voltage. So basically, the voltage at which we should stop discharging the battery in order to not damage the cell. And the CEDV is a gas gauging algorithm with a compensated end of discharge, enabling to have accurate measurement of the capacity even when the current load is changing. So then now that we know a bit more about the cells, there is some parameters that needs to be taken into account, and why do we need them? The first ones are about safety. So over voltage, over current, over temperature. Those three, if they are not monitored and if no action are taken care when they occur, may lead for the cells to malfunction, to be damaged, to explode, or to catch fire. So those are really the ones that are safety critical. Two other cases that are more related to the user experience, meaning those will not directly lead to a safety problem, but more to an end user bad experience, is, for example, under voltage and cell imbalance. Under voltage means that, as I mentioned before, the voltage should be of each cell between 4.2 and 3 volts. If we go below 3 volts, it's not dangerous, but that means that the cell will be damaged and we cannot use it with the same capacity in further cycles. So we want to prevent this as much as possible in order that your customer do not have a bad impression of your final product because of bad battery life performance due to not taking care of under voltage. Cell imbalance means that, for example, if several cells in series are there and one cell is fully charged, one cell is fully discharged, we will never be able to either charge or discharge further this battery pack because one will always reach the over voltage, one will always reach the under voltage. So what we need to do is to do cell balancing in order to bring the pack to a similar voltage to be able to extend the battery, the lifetime of the full battery pack. Also, cell balance allow to use sometimes cheaper cells or cells that are not directly matched voltage-wise when you receive them for the first time. That means that maybe you can correct this imbalance and then have the best experience for your full pack. So what those parameters means that we need to have whatever the solution we use later on, it's really advised to look at the voltage of the full pack and also of each of the cells, of the current coming in and out of the battery pack, and of the temperature. So now what are the problematic, or what is the problematic that we should take care for drones, or for battery pack for drones specifically? The first one, of course, is small form factor. We want to have a solution that takes the less space and weight as possible. We want to have solution as low cost as possible, but low cost not meaning a bad solution, but meaning the best solution that we can have for the cheapest price. And one of the other problems we have to assess, and I touched a bit on it already earlier, is how much capacity remains in my battery pack. For drones, this is critical because for other end equipment, if the battery is low or is empty, then the end equipment stops working, which is not a big deal. We just need to recharge and we are good to go. For a drone, if we are mid-flight and the battery is empty, the drone is falling. So we need to be able to predict when the battery needs to will be discharged, when you need to come back, that the drone can then land safely. Except one thing to take into account for drones is that we have a high discharge current and a non-continuous one. So as I mentioned before, if we go up or down or accelerate or brake the drones, the discharge profile will vary. So that's why we need to have something which is good at high discharge current. And here, for example, a CEDV, so compensated end of discharge voltage, have good performance with discharge between 1C and up to 25 or 50C. So this is a solution that we took in one of our TI design. And this solution that we propose also we could use with impedance track, which is the next step into the accuracy. So in case of we want to have a good and accurate solution is not enough, we want to have a really good and really accurate solution, then impedance track would be the way to go. How many cells in series do we speak of? Usually between 2 and 4, maybe up to 7 cells. The solution I will show today is focusing on the platform between 2 and 4, but we have other solutions for higher number of cells as well. And of course, as a TI design, we want to provide you something easy to evaluate, where we have the full description on how did we do the design, what was the consideration for each of the parameters, and what do we provide you is also a full Altium file that you can have, Gerber file, test report, and so on. So now speaking more in specific about one TI design, the TI-DS 00984. This TI includes includes for 4 cell. It also exists in 2 cell version, which is the same solution, just configured differently. It includes a battery charger, a CEDV, compensated end of discharge voltage, battery fuel gauging. This part is pin-to-pin compatible with impedance track if you need to have even more accurate performance. A battery pack protection, a battery cell balancing, an onboard state of charge. So we know exactly how many percentage of remaining capacity is there. And a SM-bus communication for advanced status update. So SM-bus, if you're not familiar with it, is I2C with additional communication protocol. Some of the key specifications for the charger. Here we have 93% efficiency charger with an input voltage between 18 and 28 volts DC. The charging voltage would be 16.73, which is slightly below 4.2 volts per cell. This is a charge voltage measured. This is a charge current measured at 1.311 amp. During the charge, the maximum temperature that the board is reaching is 43 degrees at close to 24 degrees C ambient temperature. This charger also has a pre-charge mode. So what is pre-charge is normally, and this was if we correctly protect our battery pack with under voltage, we should not need this function, but sometimes it may happen that the voltage of the cell go below 3 volts, which is not advised but can happen. And if we are, let's say, between 2 and 3 volts per cell, the charger will recognize this case and will then apply a really small current to safely reach 3 volts. And once we have 3 volts, then we're in safe condition and then we can start charging at a normal rate. So this is a pre-charge function that the charger includes. Then looking at the protection, we have several levels of overcurrent. For example, at 15 amp for 20 seconds, 20 amp for 10 seconds, 24 amp for 15 milliseconds. We also have then short circuit protection, like 33 amp for 1 millisecond or 44 amp for 244 microseconds. All those parameters in both value of current and of time can be programmed at different levels according to what are your specific specification, as well as the over voltage and under voltage protection and temperature protection. Some other specification for this board, we have idle current for the gauge and the regulator, with the gauge being active of 1.32 microamp. We have onboard 3.3 volt DC-DC regulator. The protection FETs that I will show you shortly after have 0.0325 ohm series impedance, and during discharge at 10 amp we have maximum of 72 degrees C. So here is how the block diagram is looking like. So here we have the connection to the cells to measure each of the cells voltage and do the balancing. We have the battery plus and minus connection, the pack plus and minus connection. So the battery is connected to the cells, and the pack is then going to the rest of the system. We have also input for thermistor for both the gas gauge and for the charger. The gas gauge is taking care of the gauging, protection, and balancing, and control the two FETs. Those two FETs are on the high side, meaning that we are not losing communication during a fault. They are back-to-back FETs, meaning that if a fault happens during charge, we can still discharge, but not charge. If a fault happens during discharge, this one will act as a diode, so we cannot discharge further, but we can still charge. If we have another problem, which is not overcharge or undercharge, over voltage or under voltage, then both FETs will open and we can neither charge or discharge. Here we have 18 to 28 volt DC input for the charger. We also have onboard 3.3. It also exists in, we can also do it as a 5 volt DC-DC regulator, and this is then going to the communication connector for the SM bus communication, and on the board we also have a couple of LEDs to show the remaining capacity. Here's how board look like with the different connector I just mentioned. So then now looking quickly into some of the test performance. Here is a charge and discharge cycle. Here we can see that during charge we have a constant current phase. Here, and during this constant current, the voltage of each cell, as we monitor all of them, is going up. When we arrive to our end of charge voltage, then the charger switches from a constant current to a constant voltage, and the current is then going down until we arrive to end of charge current. Looking to the discharge, we have here in red the current that we apply to discharge. So we have 0 at the beginning, and then we apply 10 amp, and then we go back to 0. During this time, the voltage of the full battery pack is then going to full, then going down up to the moment where that we remove the load, and the voltage is then going back up. Do not pay attention to this small bump. This is due to our load, that when we release the load, actually we had another small spike. That's why we have this small voltage bump. But what is important or interesting to see here is we can see that the voltage is here, and once we remove the load, we can see that the voltage is then going back up. And this is what I mentioned before, that due to the impedance of the cell, once we remove or add a current, then the voltage drop will apply. Here is the temperature of the MOSFET during 10 amp discharge, and here we can see that the state of charge is going from 100% to 0, and here we can see that the maximum temperature is then 72.5 degrees C. And this is a thermal picture of it, of the 10M discharge, and during the 1C charge with a spike at 47.7 degrees. This is a one-pager. Most of it already mentioned. What I would like to emphasize again is that this solution is also possible to use not only at CEDV algorithm but also impedance track in case of we need more accurate to estimate more accurately the remaining capacity. But the CEDV algorithm that we use is really appropriate or should be already good enough for most of the drones applications. We have integrated cell balancing. We can program fully all the faults for voltage, current, temperature, charge time, the charge and discharge FET, and so on. We can diagnostic lifetime the battery pack, and due to a kind of black box recorder of your battery, because we know all what's happening, so basically we can really know what happened, what went wrong, at what moment, and why. And we also have the DC-DC regulator on board. You can then go online to then look at the different datasheets or look at the tool folder where you can find schematic, bill of material, Gerber, software, the full design guide explaining how to design it. And with this, I would like to thank you all for your attention. Just before opening it for questions, a couple of links that are interested for both presentations. So on the left side is more the part covered by Kristen, showing a couple of TI design, showing three-phase ESC. So the 916 that he showed today, but also the 643 could be of interest. A couple of product selection for three-phase motor driver from Texas Instruments, and a link to have a look and download Instaspin FOC. And one training really interesting and really complete about motor control is also there. About the battery pack, the 2S, I think I know for sure that the link for the 2S is already working. For the 4S solution, the one I showed today, the link should be live in the next couple of days. But already with the 2S and 4S, it is the same solution, it is the same or really similar performance. So if you need something as of today, you can directly look at the 2S. The 4S will be there in a couple of days. And then other solutions that have different structure, how to use a gate gauge, a protection, and so on. We can look at the TIDS00553. And also of interest, maybe it's up to 10S, but it can be scalable to 7 or 5 or below 5S as well, the TIDS00449. And with this, I guess we can then open up for questions.
I see two questions already. The first one is, have you done any studies on characterizing the individual battery performance in order to build a matched battery pack?
Could you please repeat the question? So if we...
Have you done any studies on characterizing the individual battery performance to build a matched battery pack?
No, and this is because, as I mentioned, this design includes cell balancing. That means that the cell may not match the first time we connect them to the electronics. But over time, due to cell balancing, the cell will then match. So this is what I mentioned with cell balancing, that it's something that may help to save some of the costs, because you may not have to pay always for the best matching cells, as we will, due to balancing, we will make them match over time.
The next question is, can can the charger identify when one cell is failing?
The charger, no, but let me go back to the block diagram. The charger, no, because the charger only sees the full pack, but the gauging protection, yes. And this, once something will happen, for example, one cell is failing, or there is a short circuit happening, or anything, this will be identified and also communicate through SMBus. So that means that, for example, it can communicate to the rest of the drone, and you can have a communication, or you can identify then later on what happened and on which cell and what happened. And the thing is, it will be protected, but this part will be able to identify what is the problem and communicate about it.
So I see the next question with the difference in power used by a drone using FOC control and trapezoidal control. So it's kind of a difficult question to answer. If you take the theory, the control theory, FOC control should bring you up to 10 to 15% more, with the but here, that of course here you need to ensure that the motor you're using is not trapezoidal wound, it's sinusoidal wound, so you have the best performance for sinusoidal control. And also here, this is from a theoretical standpoint. When you, with your trapezoidal control, has a lot of additional algorithms included that will improve the efficiency, and you don't have the same amount of, let's say, efficiency improvement on the FOC control, of course here you will also see a mismatch on this. But if you really are able to compare an apples to apples control, which is pretty much almost impossible, you in the end will always be able to get a little bit better performance from the FOC control. But putting a number in it, I don't know. It's something that we want to look into and do a real comparison. So it's something that will happen, or we want to do these tests and also do a comparison where we say it's an apples to apples comparison and not a we don't know what the one control is doing and the other one is being super efficient. Then it's not a real true comparison, and this is why I'm a little bit fishing on a real answer.
Does anyone have any more questions? Yes, there's one that came up. Is there cell balancing during discharge?
No. Because I don't think that basically what we have to look into cell balancing is it's not a one-time thing. It's not we have an imbalance and over one cycle we completely overcome the mismatch. It's more something that will happen during charge, and for several reasons, and I will come back to this, but it's more something that is occurring over several cycles. So because the thing we could do, or it can be done in really quickly by over-dimensioning the cell balancing. We can make it extra circuit to make it with higher current, but I would not advise for it because more we do the cell balancing and more we may age the cells if we overdo it. And that's why we prefer to do it more with smaller current and do it over a longer amount of time to do a better match of the cells. And also doing charge, we typically have a lower current than doing discharge in drones application, I mean. And during this time, we can really say we can have a better effect of the cell balancing. Also, the thing is, cell balancing is basically discharging the cell on top of whatever is happening. So that means that if we are doing charge, we may add a couple of minutes, not a lot of time, but add a bit of time of the charge time. But during a charge time, it's not critical because the charger will just be connected for a couple of more minutes. During discharge, that means that the runtime is impacted directly. That means that the drone, if we try to artificially discharge additionally the cell, the overall runtime of the pack is even lower. So that's why we do not do discharge during, we don't do cell balancing during discharge. We will do it sometimes according to the algorithm of the balancing. It could be done either during idle, but the best moment to do it is during charge.
It appears there's no more questions. So that concludes today's webinar. I'd like to thank Kristen and Kevin for giving really a great presentation. And I also like to thank everyone who has attended.
Thank you.
Thank you.